This is Ken the Metal Professor, back after a month and more of a hiatus, otherwise known as laziness, and just getting lost in the holidays. But also with the holiday break in the U.S., the traffic on the math subreddits kind of slowed down a little bit. There was still a lot of stuff there, but sort of less that I was able to really zoom in on. But I've been interacting with a few, and just yesterday I came across a post that was asking about partial fractions. So I thought that would be a good subject to try to get my mojo back with interacting online and also making something that other people can get use out of from that conversation, people that might not just be hanging around on Reddit. So the interesting thing here was that this user was posting in the pre-calculus subreddit, meaning I think that they were discussing how to do partial fraction decomposition in pre-calc, which is actually pretty cool because in calculus 2 by most common breakdowns of calculus, when you start doing the more complicated integration techniques, not just the power rule and simple trig functions and stuff, but get to things a little bit more sophisticated, you encounter partial fractions. And if you take a survey of people that have been in Calc 2, they might say this was the worst thing they did, or at least second worst behind trigonometric substitution, because that's pretty awful. But if you learn the algebra of partial fractions in advance, that takes a lot of the sting out of the topic. And in fact, partial fractions is probably the epitome of the idea that calculus is only hard when you encounter hard algebra. Calculus is easy. It's the algebra backups that become hard and where people lose lots of points very often. And this is a good example of that. So the question at hand was not a calculus question. It was just find the partial fraction decomposition of this particular rational function. The denominator is already nicely factored, which is good for us. Okay, the idea of partial fraction decomposition is to look at this and say, look, there's three terms multiplied together in this denominator. So we could see this clump as the result of taking some individual smaller terms, finding a common denominator of all of them, and mushing them back together. And so partial fraction decomposition is basically placing a stick of math dynamite into this rational function and blowing it up back into its original smaller functions. So the original individual denominators that could have mushed together to produce this as the common denominator would be the terms that we see, the x plus 1, and the x minus 5. And so the puzzle that we have to solve is to figure out how this mess could have been the result of taking something over x plus something over x plus 1 plus something over x minus 5 and adding those three things together by finding a common denominator and then producing this. And again, when we get to calculus, the idea is that then to integrate this function on the left, it's the same thing as integrating three smaller functions and then adding up those results. Now, the numerators that we're looking for are mysteries. They are unknown. And so we put unknowns in for that numerator, and we'll call them A, B, and C. These are constants in this problem. The idea here is that we are going to assume that we've blown this function up into its smallest possible and most simplified terms. So, for example, if this numerator on the middle term, say in an intermediate stage, was x minus 2, that means having the same degree as the term in the denominator, we could actually divide that out function-wise and write it as 1 plus something else with lower order terms. So we're assuming that these terms have been as simplified as possible. They're canceled down as far as possible. And that means that the numerators need to be 1 degree less than what's in the denominator. And since all three of these denominators are linear functions, then in the numerator, the worst case scenario is that the mystery numerators are going to be constants. Now in other problems, let's say this denominator was x squared plus 1. Well, that denominator can't be broken down any farther. So the presumption would be that the mystery numerator could at worst be if the bottom is a polynomial of order 2, x squared plus 1, the numerator could be at worst a linear function. And so we would put in a template like bx plus c to that numerator to figure out the mystery pieces. But for this problem, 3 linear denominators, so 3 mystery numerators, which are at worst constants. Okay, now the calculus part for people that have gotten there is if we can write this mess as a sum of 3 smaller functions, then we can integrate the thing on the left by integrating the thing on the right. And what you know about calculus, if you know it so far, is that these integrals are actually really simple. They're just natural logs. Okay, so if we can learn A, B, and C, then we're done, right? The calculus part is right here. That's it. It's as easy as the calculus gets. In fact, I actually recommend doing the calculus first and then going back and discovering what the constants are afterwards. Okay, because otherwise it's too easy to get lost in the constants and then you lose track of the calculus. We're done with the calculus. If we are integrating this function, as soon as we discover these mystery constants, we're done. We have our answer to the integral as well. Okay, we're not going to worry about the integral. We're just doing the algebra here. All right. So the idea here is that that mess back there, this thing right here, this template, that's gross because it's got all sorts of fractions in it. Nobody likes fractions. So can we get rid of the fractions? And the answer is yes, we can. How do you get rid of fractions? Well, you multiply both sides of your expression by something that's going to cancel all the denominators. And in a partial fraction decomposition like this, the original denominator will cancel every denominator on both sides of this template. So we're going to take both sides of this equation and multiply it by x times x plus 1 times x minus 5. My dog is down here pawing at me because he wants attention. So on the left-hand side, the denominator is going to cancel itself and we'll just be left with 4x squared minus 5x minus 15. On the right-hand side, we distribute this multiplication through, but every time this denominator hits one of these terms, something is going to cancel. So when this denominator multiplies through and hits this term a over x, the x's are going to cancel. When it hits this middle term b over x plus 1, the x plus 1s are going to cancel, and so on for the c. And so the left-hand side reduces to the original denominator. The first term with the a, the x's cancel, you're left with the other 2 bits. For b, the x plus 1s have canceled, you're left with those other 2 bits. And then for c, the x minus 5s are going to cancel, and you're left with x times x plus 1. Okay? Now, how do we use this to discover a, b, and c? Well, there's 2 methods, and I'll show you both. The first one is to just remember that this equation has to hold, period. Which means it has to hold no matter what value of x we're talking about, anytime. For every value of x, this equation needs to be true for the correct a, b, and c. So imagine some nice values of x that we could test this equation out for, because there are some clever values of x that will wipe out many of these terms. There are 3 clever values. Okay, so for example, I've highlighted the two instances of x plus 1 on this right hand side. So imagine if we tried out x equals minus 1. It would eliminate the terms with the a's and the c's. If we plugged in x minus 5, it would eliminate the terms with the a's and the b's and leave behind the one with the c. And similarly, if we plugged in x equals 0, it would eliminate the terms with the b and the c and leave behind a. So the 3 clever values of x to plug in are just the zeros of the original terms in the denominator, -1, 5, and 0. So let's plug them in one at a time. If we plug in -1, here's the original expression. I've still highlighted those x plus 1s. Those are going to become 0. We just plug in -1 everywhere there's an x. Now this whole term is going to be, this term becomes 0, -1 for x, -1 for x. I mean, you know what's happening here. We're just plugging in -1 for x across the board. But the point is that 2 of those 3 terms on the right-hand side are going to collapse to 0. On the right-hand side, we'll end up with a net value of -6. And on the right-hand side, 2 of the 3 terms are gone. And 6b is left. And so now we know that b is -1. Ta-da! All right, now we can carry that value of b back to our expression because we've discovered it has to be -1 for this thing to work out. So here's our template again. Now this time I've highlighted the x minus 5 terms. I've plugged in -1 for b, and I'm also plugging in 5 for x. This shakes out like before. 60 equals 30c, so c is 2. Now the dogs are barking. Every day. Every time I do this, they can be quiet for 11 hours out of the day, but the 20 minutes that I'm trying to put one of these things together, blah, blah, blah. But I think my wife just got home, so they're excited. Third case, I've highlighted the terms with just the x. We've learned that b is -1 and c is 2, so let's plonk those values in as well and also plug in x equals 0. This shakes down to a is 3. And now we know that a is 3, b is -1, and c is 2. So that's the original partial fraction decomposition. Just put in a 3 there, a -1 there, and a 2 there, and you're done. If you're in calculus and you're integrating this thing, well, now you already know how the integration's supposed to turn out. We knew that before we found a, b, and c, and so we just plugged those numbers in. Now this plus d is just the arbitrary constant. Normally you would call it plus c, but that c was already reserved there. Okay, again, the calculus, this is it. This is the easy part of this problem. Calculus is easy, algebra sucks. Okay, now the second method to discover these missing coefficients is to take this mess on the right-hand side, having multiplied both terms of the original partial fraction template by the big denominator. The whole denominator canceled from the left, and then on the right, one thing canceled with each term. So we're kind of hitting the reset button. We're going to multiply out the right-hand side. So this term here, the x plus 1 times x minus 5 generates that quadratic. X times x minus 5 is just x squared minus 5x. X times x plus 1 is x squared plus x. Now look at the left and right-hand sides. On the left-hand side, there's a coefficient of x squared, there's a coefficient of x, and there's a constant. In net, on this right-hand side, we can collect a single coefficient of x squared, a single coefficient of x, and a single constant. And those things have to be equal from one side of the equation to the other. Okay, so here I've gathered the coefficients of x squared, so a plus b plus c. There you go. I've gathered the coefficients of x, -4a, -5b, and 1c, and there we go. There's a coefficient of x on the right hand side, and then the constant term is -5 times a. Every one of those things has to equal its counterpart on the left, and so we know, for example, that a plus b plus c has to be 4. -4a minus 5b plus c has to be -5, and -5a has to be -15. Okay, so we pick out those three equations. A plus c is 4. -4a minus 5b plus c is -5, and -5a is -15, and now we get to solving. The bottom equation gives us a equals 3 immediately. Okay, so let's load that back into the top two equations. Put in 3 for a in the leading terms. Let's gather the constants on the right-hand side. Now we're down to two equations and two unknowns, and okay, if you're in calculus or even pre-calculus, you should be able to solve this system of two equations and two unknowns. And it will give you b is -1, c is 2. And so a is 3, b is -1, c is 2. Same solution as through the first method. You just pick your favorite. Okay, and again, if you're doing the calculus part of it, there it is, all over again. Okay, I'll tell you the secret to solving this two equations and two unknowns. There's two methods. There's elimination and there's substitution. Elimination is when you multiply one of the rows by a constant so that you can add it to the other row and something drops out or is eliminated. So if we take this top equation and multiply it by 5, 5b plus 5c equals 5, and add that to the second equation, 5b plus -5b, the b's are gone. 5c plus c is 6c, 5 plus 7 is 12, 6c equals 12, c is 2. Okay, and then you can substitute that back into the other one. The way to do substitution is like solve this top one as c equals 1 minus b, plug 1 minus b in for that c, shake it out for b, and then use that value to go back for c. But either way, you'll get the same numbers. Okay, so I decided to add that as a sort of bonus to this, but we're done. We've done 2 methods for partial fraction decomposition. They both work no matter how complicated the systems get. Just make up clever values of x to plug into your partial fraction decomposition after you've cross-multiplied by the original denominator and learn the constants, or multiply everything out and match coefficients of the constant x, x squared, x cubed, x to the 4th. If you have all of those things, match them on both sides of the equation, pile them up into a system of equations, and get solving. Maybe I'll make another video tomorrow where I'll do something with a quadratic in it instead of just the ones where we ended up with these linear denominators, because that's where it gets a little bit more interesting. Hope it helped. Like I said, it's been almost a month and a half since I did one of these things, so a bit rusty. That explains the little jump there at the end, because I got myself derailed and had to go back and jump in again. So there's a not quite smooth transition. That'll happen. Okay, thanks for watching.